Right, good morning, guys. Today's our topic is the velocity analysis of the mechanism. The mechanism part, which we have already done in the last topics or the last sessions, in which we learned about what is a link, what is a kinematic link, what are joints, what are pairs, chains, what is the difference between a machine to a structure, and what is mechanism, and how what are inversion mechanisms and different types of inversion mechanisms for four-bar chains, a single slider chain, and double slider chain mechanism. So now the topic is, as we know that we are explaining that links are moving relative to each other. We should also define the velocity or the velocity analysis part, how we can define the velocity analysis, how you are analyzing the velocities of the links there. So before going to the velocity analysis part, we should know actually the types of motion can any link can carry. That means if you see, if you are considering any body, the body has simultaneously motion of both rotation and a translation. Taking example of a car wheel, which is when a car is moving, obviously the wheel will start rotating and it will also translate, because if you want to change the direction or the course of a car, the tire should move in a translatory way by rotating itself. So the motion there can be have a combined effect of both rotation and also translation. We are taking a simple link here, which is AB. You can see the AB link here, which moves from initial position AB to A1 B1. That means it is moving from AB to, this is our final position A1 B1. If you see here, if you consider this, a little consideration is so that link is neither completely motion of translation or completely rotational, but it is a combination of both two motions, which is translational and rotational. That means to to come from AB to A1 B1, first it should move from AB to A1 B1, right? That means it moved from AB to A1 B dash. That means this is something translational. So from here it rotated through an angle, so it became A1 B1. So it is not completely translational or completely rotational. It is a combination of both the translation and rotation. That means the link first has to move translatory from AB to A1 B dash. That's what I said. It moves to translation from AB to A1 B dash. Then it is moved from rotational with A as center. It is moving from B dash to B1 with some angle, which is rotation. So here we have both the translational and also rotational parts. If you see the second diagram here, in this, the length AB has to first rotate. That means this is the length AB. At center A, the point B or the link B rotated through an angle to B dash. Now from here, that means from A B dash to it moved translational to in this direction to A1 B1. So in the first case, in the A diagram, it first translated and then it rotated. The second case, it rotated and then it translated. So what exactly we are going to define here is, to define any relative motion of any mechanism, we cannot define the motion with completely rotational or completely translational. But this is what theoretically we go. But in an actual practice, what we do is, in actual practice, the motion of a link AB is gradual, that it is difficult to see two separate motions. But because in an actual way, this is theoretically so well, that's why we divided that into from this point to this point, this is translational, and from here to here, this is rotational. But in actual practice, it is difficult to separate them. You can't see them separately, where the translational and the rotational part. So what we consider here is, we are only considering it as a pure rotational purpose. That means, but we can't see two separate actions there, but we see two separate motions through point B, which moves faster than point A. Right? We can't see two separate motions, but we can see two separate points there. That means if you see, this B point is moving faster when compared to A, or we can see the change in the motion with respect to this point B, which is moving faster than point A. That's what we are defining here. So we are telling that we can see two separate motions through point B, which moves faster than point A. Thus, so this combined motion of rotation and translation of link may be assumed to be motion of a pure rotation about a center I. So as we are defining a motion, it is having both the translational and rotational. The problem is we can't see two separate motions in actual practice. We can only see two separate motions through a point D. That means we are considering a particular point, and we are defining the total motion as only pure rotation through a point. In some cases it might be B, but we are defining it as a center, which is known as instantaneous center, also known as centro or virtual center. The position of this instantaneous center may be discussed later, but I think you are understanding it, right? Because the link can have both translational and rotational motion, but you can't see two different motions simultaneously. But you can find the difference of a particular point or a joint in a link while it is moving. So we are defining that point or some center to define the complete motion, which is known as instantaneous center of rotation. And we are considering the whole process in the form of a pure rotation. So this is how we are considering it as only pure rotational. Let's see. Since if you see here, we have points A and B. This is A and this is B, link AB, right? Which should move to A1, B1. So it should move from AB to A1, B1. So it moved from AB to A1, B1. Again, I'm going to the same topic. There are both translational and rotational portion, but we are only considering the pure rotational. Okay. Here, if you see, it is moving from AB to A1 and B1 under the motion of rotation because we are only considering the pure rotational. Therefore, the position of center of rotation must lie on the intersections of right bisectors. That means if you see, if you draw a line here, this is a chord, right? Now this is a chord. We know bisectors, right? Bisector means dividing that into two equal parts at a right angle. That means if you see, this line is dividing this B1 into two halves at right angle. The same way, this line is also dividing which line the chord A1A is divided by this line at halfway through at 90 degrees. Now, if these two right bisectors meet at a point which is defined as our instantaneous center, that instantaneous center of rotation will define the total motion of a link AB to A1 B1. Once again, explaining the same thing. We have a link AB. It is moving from AB to A1 B1. There might be translational and rotational simultaneously, but in the previous section we defined it as we are only considering it as a pure rotational part. So we have to define a center for the rotation. So for that, what we are doing, we have a chord from A to A1, B to B1, and we should divide these chords into two equal parts by a right bisector. Right bisectors means we divide the chord into two equal parts at right angles. Now these two right bisectors will meet at or intersect at a point I. This is defined as our instantaneous center through which our center of rotation takes place. Right? That means the position of link AB goes on changing. Therefore, the center about which of motion is assumed to take place also goes on changing. Right? If the link AB motion, if it goes on changing, the center which we are assuming as a center of motion which also goes on changing. That means the instantaneous center means at that instance. That means the link which is at a position, if it is changing at that instance, the center is defined as instantaneous center. Okay. We can also define it as some center. What actually we going to define here? Three things. First one is the link may have both translational and rotational motion, but we are considering it as only a pure rotational part. To define the rotational part, we need a center through which the center of rotation takes place. We defined it as instantaneous center. And if definitely there will be a motion or the change in motion of position of the link. With the change of a link, your instantaneous center will also definitely change. You can also define that instantaneous center as centroid. This is what instantaneous center is defined as. Now we have here space centroids and body centroids. We take a small example to define what are those. You take a rigid body in a plane motion related to the second rigid body. That means we are taking a body A1, B1. You are taking another body A2, B2. both are rigid bodies which are related to each other. Okay, and they're supposed to be fixed in the space. They're fixed in some space, and they also have some instantaneous center. Okay. Assumed to be rotating about instantaneous center at a particular moment. Instantaneous. What is instantaneous center? I explained you just. Here we are telling that the instantaneous center is a point of a body which may consider fixed at that particular moment. That because the body is rotating at a particular point is defined as instantaneous center. We are assuming that both links are not changing its position. So the instantaneous center will also be but constant or the some center. If the links changes, the instantaneous center will also change. Now, as we having two bodies here, two rigid bodies, we definitely have two instantaneous centers. And the locus of the instantaneous center in the space is called as the space center. Okay? The locus of the instantaneous center in the space is defined as space centers. You can see the space centers here. This is instantaneous center 1 and this is instantaneous center 2. The locus of this instantaneous centers is defined as our space center. And the locus of instantaneous centers relative to the body itself is called as body center. That means these are instantaneous centers, but there is a locus relative to the body. Means with respect to these two bodies, there is also a locus which is defined as the body center. Okay, we have two centroids, space centroid, body centroid. Here we are considering two rigid bodies which are moving to relate to each other. So each body is having two instantaneous centers. The locus of those instantaneous centers in the space is defined as space center. That means simply we are talking about the instantaneous centers locus. But if we are talking about the instantaneous locus of instantaneous centers related to the body, that means if the both bodies are moving to relate to each other, then there will be a locus for that, and that is denoted as body centers. Okay. Now these two centroids have instantaneous center as a common point at any instant during the motion of the body. So these two centroids having a common point, which is instantaneous center, which is constant or constant point during the motion of a body. Okay, this is what space centroids and body centroids are. If you see, we are taking a simple calculation part here, which is we have I1, I2 instantaneous centers for both AB and A1, B1 and A2, B2. This is I1 and I2 for different positions of the link. Okay. Now what we are doing is then we have A1, B1 are considered curve passing distance. This I1, I2 being the space centroid, and this C1, C2 being the body centroid, which I already explained you, right? Both you have two rigid bodies, A1, B1 and A2, B2. You have I1, I2 as a space center. You have C1, C2 as a body center. Now, if you consider the point C1 here, you have consider the point C1 attached to the body linked to A1, B1, right? The same way, you have C2, which is a position which is related to point A2, B2. We have two centroids which I already explained you. One is space centroid and the other is body centroid. Space centroid is a locus of instantaneous centers, but body centroid is it is a locus of instantaneous centers with respect to related to the bodies. That means if you see C1 is attached to the body or the link A1 B1 and moves within such a way C1 coincides with I1 when the body is in the position A1 B1. And C1 coincides with I1 if body is in a position of A1 B1. The same way, C2 be the position of the point C1 when the link A1 B1 occupies a position A2 B2. Means if A1 B1 is occupying the position A2 B2, this A1 B1 is occupying the position of A2 B2. This C2 will be C1 because this is occupying this one. C1 will also occupy C2, right? That's what here we are explaining. I think you're okay with it, right? But we are showing a little consideration here. What is that? point C2 will coincide I2 only if the triangles A1, B1, C1 and A2, B2, C2 are identical. Okay, then you have two similar faces, which is A1, C1 is equal to A2, I2, B1, C2 is equal to B2, I2. Okay, this is a simple geometrical thing. I don't think we are familiar with what is instantaneous center, what are space centroids, and what is a body centroid, how space centroid and body centroid are differentiated. The basic topic which we are want to study here is the velocity analysis part. That means the point or a link velocity analysis. That means we should define how the link or a point is moving with some velocity. We should analyze the velocity part. These are done by two methods which are known as instantaneous center method and relative velocity method. Here today we are studying about the instantaneous center method, which is very convenient and easy to apply for simple mechanisms. Whereas for relative velocity method, this is for some complex configurations. We'll see it later. But for today, we are going for instantaneous center method, which is very simple to define. Right now, before going to that instantaneous center method, once again reminding you three parts. First one is we are here to define the motion of a link in the velocity analysis way. And the motion of a link is actually have both translational and rotational part, but we are considering only the pure rotational part. And for the rotational to be carried out, we need a center about which the body should rotate. And we defined the center as instantaneous center. Now we'll see how you are defining the velocity of a link by using instantaneous center method. So the instantaneous center method of analyzing the motion is a mechanism based upon the concept, which is that any displacement of a body having motion in one plane can be considered as pure rotational motion, which I explained you just now. We are only considering the pure rotational part of motion, but not the translational part, which is rotated about a center which we defined as instantaneous center or virtual center. Depending on this principle, the instantaneous center method works and we'll find the velocity. Consider 2 points AB on a rigid link. We have a link and we have 2 points A and B, right? The velocity, let VA be the velocity and VB be the velocities of point A and B. This is VA in this direction and this is VB in this direction. That means both are having some horizontal and vertical or 90 degrees part with an axis. The two points in the links having two velocities there. VA being the magnitude and direction on the direction A at point A, VB be the only the direction at point B. Then the magnitude of VB we should determine by using this instantaneous center method. That means to define instantaneous center method, we are taking a simple example. So we took 2 points in the links A and B, A having a velocity of VA, B having a velocity of VB, and VA representing both the magnitude and direction of point A. But here we are considering that VB is mentioning only direction, but not the magnitude there. We should find that magnitude by using some method. We have two methods we define: instantaneous center and relative pole method. Now we are seeing instantaneous center. We are drawing the diagram I show you. We draw AI and BI perpendicular to the direction VA respectively. These lines intersect at a point I, which we defined as instantaneous center or virtual center of the link. Since A and B points are rigid links, therefore they cannot have a relative motion between them. So we should define the instantaneous center part. So we are drawing two perpendicular. We said that, right? We should draw some right bisectors. So this is the right bisector at point A. This is the right bisector at point B. So they both met at a point which we defined as I, is instantaneous center. That is what the instantaneous center. And about that point, the whole link will start rotating, right? And we divided both the velocities into two things. We have a velocity, we have a angle, we define some angle there, which is alpha for at point A and beta for at point B. So we divided this into V cos alpha in this direction, and V sin V B cos beta in this direction. It is simple geometrical or trigonometrical part. VA with an angle alpha is divided into VA cos alpha, and the same way VB with an angle beta is divided into VB cos beta. What we are assuming here is, as both are moving relative to each other, both velocities should be same. That means VA cos alpha is equal to VB cos beta. Cross multiplying them, we have VA by VB cos beta by cos alpha. We can write cos beta as sin 90 minus beta, and this is a sin 90 minus alpha. I think you know from the trigonometry. Now we'll take a triangle there, ABI, and we'll see the Lamis theorem. I think we know what is Lamis theorem. We have the single point, we have three different forces acting here in the Lamis theorem. This is an angle alpha, this is an angle beta, this is an angle gamma. So what if this is a force P, this is force Q, and if this is force R. Lamis theorem explains that the force to the opposite sine angle, that means P by, which is sine, angle opposite to P is alpha, which is equal to another force Q, which is opposite sine, angle opposite to Q is sine beta. So this is what our Lamis theorem is. You can see from the triangle in the previous section on the previous slide, the diagram, we can write this triangle. How I'll show you. I think you understood what is the Lamis theorem is. We are taking a triangle ABI. This is the triangle ABI. From here, we have a force AI, we have force BI, we have an angle 90 minus alpha once, we have an angle 90 minus beta here. With those, we are having the sine or Lamis theorem here, which is AI sine beta sine 90 minus beta, BI sine 90 minus alpha. Cross multiply again, you will have AI by BI. We have an equation here, we have another equation here. So if the sine 90 minus beta, sine 90 minus alpha are equal, you will have VA by VB is equal to AI by BI. So VI by AI is equal to VB by BI, which is gamma, because we know V is equal to R omega, right? That means V by R is equal to omega. If you see, this is V, which is velocity, linear velocity. R is some distance or displacement. If it is having AI, you take it as a radius, right? Which is equal to omega, which is angular velocity. If you see, if you also have an any other point C here, you can write it as VC by CI. If you have an any other point VD, take it as VD by CI. If the number of points are increasing, but the ratio or the constant here will be the same, which is velocity by the radial distance will always be equal to the angular velocity. Okay, this is what instantaneous center is. So from the above equations, we find two things here, which is VA, if VA is known magnitude and direction, VB we only know the direction. The velocity of point B or any other point C lying in the same belt will be determined by the direction, magnitude direction. That means if you see the equation which we wrote there is VA by AI is equal to VB by BI, right? If you want to find VB, take this here, cross multiply here. If you know this AI, BI, and we mentioned that we know the magnitude of VA, we can find VB obviously. This is what we can find. This is how we can find the velocity of unknown points of a link by using instantaneous center method. Okay, but we should find out what are the properties of this instantaneous center. How can, what basically the properties is, the rigid link rotate instantaneously related to the other link. If you have usually two, we are taking two links which are related to each other, the rigid link rotates instantaneously related to the other link about the instantaneous center. That is what we are defining instantaneous center. It is a basic property of a mechanism when you are defining instantaneous center. And the other one is, the two rigid links have no linear velocity to each other at instantaneous center. At instantaneous center, there is no linear velocity for the two rigid links. These are very important two properties which we should remember when you are going for an instantaneous center method. Right? Clear? The first one is, one link is always moving relative to the other link. The second one is there is no linear velocity at the instantaneous center for the two links. Those are two things. The next one is we should find out the number of instantaneous center for any mechanism. We should find out, right? If you have a 4-bar mechanism, what how many instantaneous centers we have? We have 5 bar, 6 bar. The formula for that is n is equal to n into n minus 1 by 2. This is number of instantaneous centers, and this one is number of links. If you see, this is the 4-bar mechanism. That means the equation will be 4 into 4 minus 1 by 2, which is 6. That means in a 4-bar mechanism, how many instantaneous centers we having? 6 instantaneous centers. If it is a 5-bar mechanism, substitute 5 into 5 minus 1 2. If it is 6-bar mechanism, go in 6 into 6 minus 1 by 2. I think you understood the topic there. Now, next one. How many types of instantaneous centers we have? We are taking an example of a 4-bar mechanism here. We have 3 types of instantaneous centers: fixed instantaneous centers, permanent instantaneous centers, neither fixed nor permanent instantaneous centers. Fixed instantaneous is fixed related to fixed link. Permanent instantaneous means other than the fixed link, that those are permanent. Something which are neither fixed nor permanent. We will take an example in this. This is the 4-bar mechanism, the formula for this to find out number of instantaneous centers, which I already mentioned here. So we have 6 instantaneous centers here. This is link 1, link 2, link 3, and link 4. This is I14 because it is forming a center with 1 and 4, right? This is I12. It is forming with 1 and 2. This is I23 with 2 and 3. This is I34 with 3 and 4. If you extend these two lines here, you can see I13 here. Okay, this is 1 and 3, right? This is 1 and 3. In the same way, if you extend these two here, you can see I24, right? Because this 2 and 4. So how many instantaneous centers we have? 6. So we are done with 6. 1, 2, 3, 4, 5, and 6. So we divided this instantaneous centers into 3 categories. The fixed instantaneous centers. I think it is very easy for us to define the fixed instantaneous here. The fixed instantaneous here are here this I14 and I12 because they are the fixed link, right? Those are our fixed instantaneous centers. This fixed instantaneous centers or permanent instantaneous centers are defined as primary instantaneous. Both fixed and permanent are defined as primary. This neither fixed or nor it is the secondary type. But here in the diagram, this I14 and I12 are fixed. This I34 and I23 are permanent, and the remaining I13 and I24 are neither permanent nor fixed. These two are defined as secondary instantaneous centers. These 4 are defined as primary instantaneous centers. So our instantaneous centers are divided into 3 types: fixed, permanent, neither fixed or nor permanent. Okay. Now we'll see how we can locate our instantaneous centers. Here we have some steps to follow. So by that we can define our instantaneous centers. So rules we should follow. First one, when two links are connected by a pin joint, the instantaneous centers, that means you're talking about when two links are connected by a pin joint, that the two instantaneous centers lie on the center of a pin. Two are connected here, that the instantaneous center will be lies in the center of a pin. I will show you a diagram. Right, if you see, here we have two links, link 1 and 2, they are fixed at a point, and now our instantaneous center is at the center. This is what the first one. If you have two links which are fixed at a point, and our instantaneous center is at the center of the link. That is the first case we have. Next, second one is when two links are having rolling contact, they are rolling. The instantaneous center lies on their point of contact. If you have to have rolling contact, that here you have a rolling contact. This is link 1 which is fixed, and the link 2 is rolling onto the link 1. Now the instantaneous center will be at the point of contact. That Hence, this is our floor and some ball is rotating. The instantaneous center for that will be at the point of contact. Here it is at the center of link. Here this is at the point of contact. Okay. Now you will see the third one. When two links having sliding contact, here you having rolling contact, here we having sliding contact. The instantaneous center lies on the common normal at the point of contact. That means if you have some sliding contact at the point of contact, we should draw a common normal. Now the instantaneous center will be at the common normal. We have three conditions here. And we see the three conditions here. The first place, this is link 1 fixed, and the body is having 2 points, which is A and B, which are moving in the direction this VA and VB. Now we are drawing some common normal at the point of contact, and now here we can define this I instantaneous center, which is infinity, because these 2 points are not getting intersected at any point. But we don't know, there may be a chance at the infinite point they may get intersected, because if you see this A line and this B line both are intersecting at a point, and we define it as A12. But here they are not intersecting at a point, so we define it as instantaneous center at infinity. This is the next one. This is link 1, this link 2. Now this is sliding in this way. This is AB. This both again at the point of contact they have some instantaneous center. The difference here and the here is the link itself. Here the link is a flat one. Here you have a curved one. Now the third one, you have here the body, the link. This is a slider which is sliding in this way. The both the point of contact here at a point I12. So these are three examples for a sliding part. So this is one we having two links which are attached. The instantaneous center will be at the point at the center of point, and the second one is if they are rolling, they are at the point of contact, and for sliding also they are at the point of contact. But there we should draw some common normal to. This is different cases here. This is Arenhold-Kennedy theorem. If you have three bodies moving related to each other, in the previous sessions or in the previous topics, we are only considering two bodies. If you have three bodies moving related to each other, now they have three instantaneous center lies in a straight line. That means if you have three bodies, you have three links. Substitute in our equation to find number of instantaneous centers. So we have how many? We have three instantaneous centers. So which are, if you see three bodies, yeah, this is one instantaneous center, this is one instantaneous center, this is another instantaneous center. What we are telling here is according to Arnold-Kennedy theorem, if we have three bodies moving related to each other, so we have three instantaneous centers lie in a straight line. Very important one. If you have three bodies which are moving related to each other, then we have three instantaneous centers which lie on a straight line. Okay, that's what our Arenhold-Kennedy explains us. We have three bodies, three instantaneous centers. Then all the three instantaneous centers lie in a straight line. That's what he explained us. Now we'll see the method to locate the instantaneous centers in a mechanism. Okay, and to explain this, I am once again explaining you what exactly the instantaneous center is. We have links which are moving relative to each other. The motion of a link might be translational or rotational, but in actual practice, we are only considering the rotational part, not the translational part. To define the rotational part, we need a center about which the body is rotating. To get that center, we should draw the right bisectors, and they bisect or intersect at a point. We define them as instantaneous centers. So to find the velocity of a particular point, we have two methods. One is instantaneous center and the other is relative pole method. We are now seeing the instantaneous center method. To find the or to conduct the instantaneous center method, we need to locate the instantaneous center. So if you have the instantaneous center, so it's easy for us to find the velocity part. So we should structure a method to locate the instantaneous centers, which you know we're doing. First point, we should determine the number of instantaneous centers, which is the relation here. If you have 4 bars, you substitute and you have 6, right? The next one is we should make all the instantaneous centers in the mechanism. You see, if you have 4 bars, we made 4 links here. Now the instantaneous centers are 6 in number. So that means we should write with 1 and 2. Here we have 1, 2. Then 1 and 3, we have 1, 3. Then 1 and 4, we have 1, 4. Okay. Next with this 2 and 3, 2, 3, 2 and 2 and 4, 2, 4. We are done. Now with this 3 and 4, 3, 4. You can see here we have 6 links. Okay. So first we should define how many links we have. Then we should define the link nomenclature by using this table. And the third one is we should locate those instantaneous centers. We have 3 types of instantaneous centers: fixed, permanent, neither fixed or not permanent. So first we should locate the fixed and permanent instantaneous centers. Okay, how? If you see in this figure, we have a 4-bar mechanism. So we have 6 links. In the table will just explain you that. In this, I12 and I14 are fixed, because in the fixed link these two are fixed. I14 and I12 are fixed, and I23, I34 are permanent. Okay, and these two are neither permanent nor fixed. In the previous section I explained you that. So this is the third point. We should locate the fixed and permanent instantaneous centers. Fourth point is locate the remaining neither permanent nor instantaneous centers, which I already done. That means this I13 and I24 are remaining, or the leftover two instantaneous, which are not non-permanent and not fixed thing. With as we are done with locating all the instantaneous center, we should draw a circular diagram here. Okay, how we should find this is done by a circular diagram as shown in figure here. How? Mark points on a circle equal to number of links in the mechanism. That means if you see, this is our circle, right? What we are doing, this is a circle, then the circular diagram. Mark points on the circle equal to number of links in the mechanism. That means how many links we have? We have 4 links, right? That means in the present case we have 4 links, so we marked 1, 2, 3, and 4. So we have 1, 2, 3, and 4. So we are done there. Next, what we are doing? Join the solid lines to show that these centers are already found. That means you join I1, 2, 2, 3, 3, 4, and 1, 4. I'll show in the diagram. We joined this 1, 4, we joined this 1, 2, we joined this 2, 3, we joined this 3, 4, which are already given. We joined them. Fine, it is very good. The next point is, in order to find the other two instantaneous centers, join two such a points that the line joining from them forms two adjacent triangles in the circular diagram. Means we should combine two other centers, so that what should happen is it should form two triangles there. If you see, if you meet these two and these two, you can see we have two identical triangles in the circular diagram. So we should join two links in a form that we should get two identical triangles there. So by this we are clear that the other two links, which are neither permanent nor fixed, are 1, 3, I13 and I2. This is how we should find the instantaneous centers. Okay, I explained you once again all the points. First point here is we should define the number of instantaneous centers here. The second one is we should draw a table in this way, and we should find the links. The third one is we should find out the fixed and permanent instantaneous centers. Fourth one is we should locate the centers which are neither fixed nor permanent by using a circular diagram. And I just now explained how should we draw a circular diagram, and then by that we can find the all instantaneous centers. We'll see a simple example and we'll conclude it. Here you have for 4-bar chain mechanism. Here we have AB is a link of 300 mm, BC and CD both having same distance, which is 360. AD is having 600 mm, which is fixed link. we having an angle of 60 degrees, which is BAD. The crank AB rotate with an RPM of 100 RPM. Locate all instantaneous centers and find the angular velocity of BC. Okay. As we have an RPM or speed of AB link, we divide that into angular velocity, which is we know omega is equal to 2 pi n by 60. We have omega AB. So our first task is to locate the instantaneous centers here. The first point here is we should know number of instantaneous centers, which is n is equal to n into n minus 1. 4 into 4 minus 1 by 2, that means we have 6. For a forward cell mechanism, the table we should draw, which I already explained, like 1, 2, 3, 4. The first center is for 1 and 2. That is first link is 1, 2, and for 1, 3, so it is 1, 3, and for 1, 4, it is 1, 4. 3 centers are done. Now 2, 3. The fourth one is 2, 3 center, and this is 2, 4. The last one is 3, 4. So we are done with the table part. We define how many, what are those things. Now we should locate the fixed and permanent what we say instantaneous centers. Now this is the diagram. I12, I14 are two permanent things, or sorry, fixed things. I34 and I23 are two permanent things. It is very easy one to draw. You just draw two lines here in this way and here. They will meet at a point which is I24. Here we drawn two things which meet at a point which is also another instantaneous center. So we have here 6 instantaneous centers which are easy, right? I think you understood how to define instantaneous centers. And please go through the velocity part and please let me know after this session. Please, if any doubts in finding the angular velocity of link BC, please let me know in the message me so that we can clear any doubts. So this is what our instantaneous center method. Please go through different problems there, which is an important question for your exam point of view. The next session we will see the relative pole method, how you can find the velocity for any link.